So I would like first to compliment something I didn't say, that it was my pleasure to be here. And I think there's no real proof to give except that I am not a masochist and I am coming that often. So it means that I have really pleasure in being here. So let us go now to real job. And it's my pleasure to invite Professor Adhikari to talk about some elementary algebraic methods in the study of zero-sum theorems. Thank you very much.
So, first of all, I'd like to thank the organizers for inviting me to this conference in honor of my good friends Srini and Kalyan, and to meet so many old friends and colleagues. So, I'm writing a book with Tangadurai, and this will be finished, planning to finish this summer. So, so recently I lectured on many topics around this theme, but of course I can give many disjoint talks on this. But so, so while going through some zero sum results, apart from some combinatorial arguments, we shall have a glimpse of elementary algebraic methods tackling these problems. So these methods here, they remind me this quotation of Rota. The mystery as well as the glory of mathematics lies not so much in the fact that abstract theories turn out to be useful in solving problems, but in fact that, wonder of wonders, a theory meant for one type of problems is often the only way of solving problems of entirely different kinds, problems for which the theory was not intended. Though in many problems in additive combinatorics, this is perfectly fits in, but some results which I would see there are alternate proofs, but maybe in some places these algebraic methods may be called the proof from the book, sort of. So some definitions, and so one observes that the following this sequence of n minus 1 zeros and n minus 1 ones, this doesn't have a subsequence of length n whose sum is 0 mod n. Now the 1961 result, this can be said to be the beginning of this branch of additive combinatorics, zero sum additive combinatorics. So that says that this example is rather optimal in the sense that if you go one up, then any sequence of 2n minus 1 integers, they have a subsequence of n elements whose sum is 0 mod n. So this prototype of zero sum theorems, has several proofs, and there is an article of Allen and Dubinier where there are about 7 proofs. Now, some among the most interesting proofs involve elementary algebraic techniques. So, following along, we give proof here using the Chevalier-Warning theorem. So, the statement of Chevalier-Warning theorem, if Fq is the finite field with q elements and Fi's are a set of finite polynomials, finitely many polynomials in n variables, such that the sum of the degrees is less than the number of variables, and if trivial solution is there, then there is a non-trivial solution. In fact, precisely the number of solution is a multiple of the characteristic, that so says from that it follows. So the now we do the proof of the EZ theorem using this. Now one can see, it is not difficult to see that the important most important part is the proving for the prime case. So once you put, so by induction on the number of prime factors of n, one can get the result from once you prove for prime. So we see the proof in the case where p is a prime, So we take a sequence here length 2p minus 1 over fp, and we consider this system of equations in 2p minus 1 variables, and both of degree p minus 1, so that the sum of the degrees is strictly less than the number of variables, and trivial solution is there. So by Shivalli warning, there is a non-trivial solution. So let I be the number of those indices where yi is not 0. Now since this is a non-trivial solution, capital I is non-empty. So from the first equation, it follows by Fermat's theorem, whenever it is non-zero, it is 1. So from the first thing, it follows that summing over I belonging to R capital I, this ai is 0. But in the second one, it picks up 1 in the non-trivial places. So number of non-zero entries is just multiple of p, but the only multiple of p between 1 and 2p minus 1 is p. So that shows that, sorry, can you go back? Yeah. So that shows that cardinality I equal to p. So this is a sort of magic proof. Now, by a simple inductive argument, by the structure theorem of finite abelian groups, one can deduce that any sequence of length 2n minus 1 elements of an abelian group of order n, it will have a zero sum subsequence of length n. In fact, in this counter example, we can see when the group is z mod nz, then it is precisely 2n minus 1. The value, let us see, was that one? Okay. So for a finite abelian group, the following definitions are suggested by the EZ theorem. So capital EG is the smallest natural number such that any sequence of k elements in G has a zero sum subsequence of length equal to cardinality of G. In fact, there is more general things we can consider. Requirement maybe the length is multiple of the exponent, but here the cardinality of G if we take, then this is capital EG. Now EGZ theorem says that for an abelian group of order n, EG is less than equal to 2n minus 1. With the counterexample we had seen earlier, that gives for Z mod nz it is precisely 2n minus 1, and one knows that if it is not cyclic, then it goes strictly below, and it is n plus n by 2 if it is not cyclic but of the form, then this is realized by Z mod 2z, the cyclic group of order 2, and another cyclic group of even order. Then if it is not in this form, then it further goes down to n plus n by 3 plus 1, and that is realized by groups of Z mod 3z direct sum Z mod 3mz, like that. So some results are known like that to some extent, and so then SG is another constant which is suggested by the EZ theorem. So this is, we require the minimal length which guarantees the zero sum subsequence of length exponent G. So in Z mod nz the exponent is also n. So we have E of Z mod nz is S of that is equal to 2n minus 1. So the constant dg, we have to now another constant we have to bring. There are many constants, eta constant and Olson constant and all. They are important for various reasons, but here we will stick to those two and one more. So given any sequence of n integers, considering the sums a1, a1 plus a2 like that, this. So by pigeonhole principle, if none of them is 0 mod n, then two of them are equal mod n. So there is always a non-trivial, non-empty sequence, subsequence whose sum is 0 mod n. So one can ask this question in arbitrary finite abelian group, and in 1960s this question was asked: the smallest natural number such that a sequence of that length guarantees a non-empty subsequence, zero sum subsequence. Now this problem was asked by Davenport in a conference in YO University in 1966, but much before that Rogers published an article 62. Somehow it was not noticed by earlier researchers like Olson and others. So people, now we know it by Davenport constant. So, I told all these things. So the problem of finding dg, this was of course had an application in mind, whereas this Erdos Ginzburg G was a curious question, and this one was motivated by this, that if G is the class group of an algebraic number field and dg is the maximal number of prime ideals required in the decomposition of an irreducible integer, and there is sum which will require this many, and for everything you can fold them and bring less than equal to that. So this is important for various reasons in algebraic number theory. Now this also has application in graph theory, and also the well-known paper of Alfred Granville and Pomerance, that there are infinitely many of Carmichael numbers in 1994. They used a known bound for this Davenport constant. So the idea what is known about this, so I started at 10 or 15. 10. Okay. So clearly we know the same argument shows that dg is less than equal to n, and if we have g is the direct sum of z cyclic groups of order n1, n2, this, then writing this mg equal to this, so like 1 0 0 0 n1 minus 1 times 0 1 0 0 n2 minus 1 times etc., that gives the lower, this lower bound, and upper bound is again in this. So but I'll go quickly because lack of time. So this, many people worked on that, more or less. This is the now the best bound, whereas m is the exponent and 1 plus log. This is the general known bound. This was used, and they gave another proof, Alport, Garmin, Pomerance, in their paper. So the conjecture is that Gao and Geroldinger, that lower bound is true for rank 3 and for this type of groups, and this is established asymptotically. So fixing r and n goes to infinity. So I could have told bit more, but you have to hurry up because. So then there is another conjecture like this. So we are far from these things. Now for a finite abelian group of order n, this Gao established the following relation between this Eg and Dg. Till then people are investigating these two constants separately. Now this was proved in 1996. So I'll go quickly. So from since for this usually it is this we have observed, this easy observation by pigeonhole principle. From this theorem it follows that this EGZ theorem follows from this Gauss result. So then we started with some collaborators and some weighted. So we take a non-empty subset of this, because this is meaningful, because once you go above this, so the Davenport constant with weight A denoted by DAG is defined to be the least natural number such that any sequence there is a non-empty weighted zero sum subsequence, meaning there is a non-empty subsequence with some choosing, we can choose weights from capital A such that this becomes 0. Similarly, one defines this with the requirement that this length of the A weighted zero sum subsequence is of length mod G. Now, when you have capital A equal to singleton 1, that will correspond to the classical constants. So, let us go to G is equal to the cyclic group of order n. So, in our first paper, where it was with Chain, Friedlander, Koniagin, and Pappalardi, we took this uh, weight set and we found dn is this by pigeonhole principle, and then this took some work to deduce that A is n plus this log, as if this is n minus 1 plus this. So, this I will skip and go to some other. No, but there was. So, if we take the weight set to be the units in Z mod nz, if n is this, then take this sequence A1, P1, P1, P2, and then the product of 1 less than. So, then one can see that there is no A weighted zero subsequence, then that gives this bound. And since most often if we can choose a good counterexample, we are very near the truth. So, we conjectured that perhaps this is the truth and this is that. Do we take n minus 1 zeros and this sequence? So, then that suggests that this is greater than equal to this, but we thought that this should be the value, and this was proved by Luca next year, and then later by Griffiths by another method. So, this result was proved. So, we have from this the DAN also follows. Now, let us see the group Z mod PZ. So, then one choice of weight is this, and this by combinatorial argument one proves that DAP is this and EAP is P minus 1 plus the integral part of P by R. Then when we take this A is the set of quadratic residues, then with Purushottam we proved this DAP is 3 and EAP is P plus 2. And with all these observations, calculations in the particular cases suggested that perhaps that Gauss result is true in the weighted scenario also. And when the cyclic case with Purushottam we had a proof applying Cauchy-Davenport. Here we will see a sketch, if time permits, a sketch of the proof with later with Sauli and Purushottam using permanent lemma. So, how much time I have? 10 minutes? 10 minutes, okay. So, let us quickly go through a sketch of this proof. Now, permanent is like determinant with no sign. So, that this is very important in combinatorics. There are many results about conjectures, which results and all. So, a special case of permanent lemma is this. This is a special case. I can refer to the general one by some articles of Allen. So, take a matrix over a P minus 1 cross P minus 1, and suppose the permanent is non-zero. Then, given any sequence of P minus 1 elements in this, there is elements in 0 1 P minus 1 such that this sum is when the I equal to 1, then it is not equal to B1, I equal to 2 not equal to B2, like that. So, for any non-empty weight set, this is greater than equal to this. So, now A contains AB, because our with A B at least cardinality 2. So weight set. So A less than B, and this be any sequence of M elements where M is this. So we have to prove that such sequence has a zero sum with weight in our A. So first we assume that the number of non-zero elements in the above sequence is at least p minus 1. So without loss of generality, by interchanging, we assume the first p minus 1 are non-zero. Now consider the matrix where this is equal to b minus icj for this. Now this element we choose, and all other elements are denoted by, give them names this, b1, b2, bp minus 1, just give them names as apart from this element. Now we can choose, because see easily that permanent is non-zero. Now there are this by that theorem. Now our matrix, all the rows are same. So the same thing for every I we get same thing. So this is not equal to this for this is for any of those. Let us go. This. So this is not equal to any of these b1, b2, b this. So it has to be equal to this. So that forces that this sum, where are we? Here. So this sum has to be equal to that remaining element, because this is not equal to any of the other elements. And then we rearrange. Now if epsilon is 0, then you get ACJ. If it is 1, then this gets cancelled, you get BCJ. And last one is this. So you get a p length zero sum subsequence with weight set AB. So that gives that. Other side is simple combinatorial argument would give this. So this proves that in the prime case, Z mod Pz cyclic group of order, prime order, we have proved that conjecture, that Gauss result in the weighted scenario. Then this is another result, bit more general for arbitrary abelian groups. But again here the cardinality of A, so we are not recovering Gauss result from any of these results. So cardinality A is greater than or equal to 2, and the condition is this GCD condition. Then we have again this result holds. So that works for many. If we have in the weight set 2 elements consecutive, then that works. So and from this even that prime case trivially follows. So this, after this, then 2009 Wan and Zheng proved for general cyclic group, and Zinkiewicz, Marcha and Ordags, they proved for general abelian finite abelian group. Now the thing is that both of them uses this. This is a generalization of Kresser's addition theorem by Devos, Godin and Mohr, which came in 2009, and both of them use this. So there is no other proof. So this could not be proved before that. Not that if we had this we could have proved. So Yuan and Zheng first noticed that this is very much applicable, and then they also used this and they could. That is, proof is difficult. Okay. Then though we started our investigation as a rather curious thing to see whether get some idea about the conjectured bounds in the non-weighted case, but then later there are many people have found applications in algebraic number theory and coding theory, and this is one of the results which I had quoted, but maybe I'll go a bit ahead so I can give references of one can look into this in Google. And so many people now, there is another thing, because of these applications there people are trying to find good bounds for these constants. So we are not going through those now. Then there is another constant Sg, There are many results we had done, and there were these two variable, this conjecture remained open and Ryer proved in commutative way. But this Ronai's method was very useful. This is a linear algebraic method, and 2 3 minutes. Yeah. So I'll quickly go this. There was a Ronai idea was to construct a polynomial in many variables which vanishes at all points other than that 0 0 0 0, and there so one gets at vector 0 you have 2, and this is 0 all non-zero points. Then trivially you construct this which is also does that, but degree is different, but then that contradicts about that because these monomials these constitute a basis. So I just giving a just rough idea about what is this because I want to tell about this method little bit. So there are some references I have given. If anybody wants, I can give the slides. So we started in the weighted generalization. So I'll mention where that this is a very good result we could get, but this was a commutative method. So here the asymptotic behavior of this for a finite abelian group of even exponent. So then we get a very asymptotic result. But odd things we tried with several students earlier, and now we get this result in 2022. And if p is an odd prime and d is less than equal to 4, and you have this rank 4 abelian p group, and q is equal to qd, the exponent, then for any integer k greater than 2, that if you have this, you require a zero sum of length kq, then it is exactly equal. Whereas Ronay's method in the classical case was just, I mean, little less than, I mean, the exact conjecture. But here we could get exact values, but again with lower rank only. And when d is less than equal to 2, then we can even get SQA. So we can get the analog of that classical constant here and get the exact value. And as is clear that once you do for a equal to 1 2, you can do for any scalar multiple of the weight. So with this we stop. Thank you.